So we have talked about the formation of ions from neutral atoms. So again, atoms can either lose electrons to form positively charged ions called cations, or negatively charged, or they can gain electrons to form negatively charged anions. But ion formation by atoms is not an isolated singular process. So that is, one atom alone cannot form an ion. There has to be multiple atoms involved. So electron loss and electron gain are always partner processes. The electrons lost by the metal are the same ones gained by the nonmetal. So you may have been wondering where those lost electrons go, or where do the electrons that nonmetals gain come from. So they must come from a metal. So the metal must lose them, and there must be a nonmetal to gain them. So no atom can lose electrons unless another atom is available to gain them. So we talked about how sodium is a metal which will lose an electron, but another atom such as chlorine will gain that electron. And so we have one atom losing and one gaining, and so we have a cation and an anion being formed in this process. Now, opposite charges attract. So we'll have this positively charged cation and this negatively charged anion. And so because opposite charges attract, they will form a bond with each other, or attractive force with each other. The positive and negative ions simultaneously form from such electron transfer attract one another, forming an ionic bond. An ionic bond is the chemical bond formed through the transfer of one or more electrons from an atom or group of atoms to another atom or group of atoms. And so later on we'll talk about polyatomic ions, which is a group of electrically charged atoms. An ionic compound is a compound in which ionic bonds are present. So these attractive forces between negatively charged ions form an ionic bond. And in compounds in which these types of bonds are present, we have an ionic compound. And after these ionic compounds have been formed, their properties differ drastically from the cation and the anion from which it is formed, or which it was formed. So if we reacted sodium metal, so sodium metal, and chlorine gas, so Cl2, so chlorine gas, so there's a chemical reaction that occurs between the two, and we produce table salt or sodium chloride. And the properties of sodium chloride differ drastically from both the original metal sodium and the chlorine gas. So both sodium and chlorine are toxic to humans if consumed, but sodium chloride is relatively safe as long as you don't consume too much, which could lead to high blood pressure. But yes, so typically sodium chloride is safe. But in ionic compounds, we don't have these individual sodium or cation and anion together. Instead, we have this complex structure called the crystal lattice structure, where we have alternating cations and anions involved. So we have a crystal lattice structure instead of just a single cation and anion. So an ionic compound in the solid state consists of positive and negative ions arranged in such a way that each ion is surrounded by nearest neighbors of the opposite charge. Any given ion is bonded by electrostatic attractions, that is positive, negative attractions, to all the other ions of opposite charge immediately surrounding it. So we again have this crystal lattice structure where we have these alternating positive and negative charges. In ionic compounds, the simplest ratio of oppositely charged ions that gives an electrically neutral unit is called a formula unit. That is, the amount of positive charge equals exactly the amount of negative charge to give us an electrically neutral unit. Ionic crystals are made up of a large number of formula units that form a regular three-dimensional crystalline lattice, or crystal lattice for short, crystal lattice structure. So since we have one positive and one negative, we have exactly the same amount of positive and negative charge, and so we would need one sodium ion and one chloride anion to form the formula unit of sodium chloride, which is the ionic compound that these ions form. And so we have these repeating formula units to make up the crystal lattice structure. Ions must combine in a ratio that makes the compound electrically neutral overall. So we said that the compound must have an electrically neutral formula unit, and so we need to have the same amount of positive and negative charge. And as we saw, ions can form charges with different amounts. So for example, group 2 atoms can form or will form cations that have a positive 2 charge. But let's say that they are combined with an anion that has a negative 1 charge. So then what happens? So we have to balance out those charges. So if we have positive 1 and it's combined with an ion that has a negative 1 charge, then we only need one of those, 1 and 1, to give us equal magnitudes of positive and negative charge. Now let's say we combine lithium. So lithium has positive 1 charge, it's in group 1, and we combined it with oxygen from group 6, and the group 6 elements will form anions with negative 2 charge. So now we have negative 2 charge, and we would need 2 lithium ions to give us a total of positive 2 charge. So the ionic compound formed between lithium and oxygen would be Li2O, because we need 2 lithium ions for every 1 oxygen anion. And then let's say we had barium, which is in group 2, that has a positive 2 charge when it forms an ion. And if we were pairing it with iodine, iodine is in group 7, and so those form anions with negative 1 charge. And so we would need 2 of those in order to counteract this positive 2 charge. So then BaI2, because we need 2 ions of iodine. And then to get an electrically neutral ratio, if we were pairing aluminum from group 3 and oxygen in group 6, so 3 plus and 2 minus, then the simplest ratio would be 2 aluminum ions to 3 oxygen ions. That would give us an electrically neutral give us an electrically neutral formula unit overall. So then the formula would be Al2O3. But instead of thinking of it in terms of ratios, there's a much simpler way that we can write formulas for ionic compounds. So this is called the crisscross method. So essentially, we just crisscross the charges. So the charge of the cation, the positively charged ion, becomes the subscript of the nonmetal, or the anion. And then likewise, the charge here becomes the subscript of the metal. So because compounds are electrically neutral, one can determine the formula of a compound this way. The charge on the cation becomes the subscript on the anion. The charge on the anion becomes the subscript on the cation. But we want the lowest whole number ratios of subscripts. And so if these subscripts are not in the lowest whole number ratios, then we divide them by the greatest common factor, so that they do become the lowest whole number ratios. So let's say instead we had Mg2 plus and O2 minus. When we crisscross them, then we would get Mg2O2, but we can divide each of these by 2, so the greatest common factor, to make them into the lowest whole number ratio. So the formula would be MgO. But we'll talk about this again in some slides to come. Okay, so when the charges are not equal in magnitude, we crisscross the charges, writing the charges as subscripts and making sure that they're in the lowest whole number ratio. But like we said, when the charges are equal in magnitude, the lowest whole number ratio will be 1 to 1. So like in our previous example with magnesium and oxygen, so a little trick to help you is that when we have equal magnitudes, the ratio, the lowest whole number ratio, will always be 1 to 1. So looking at calcium and oxygen, the lowest whole number ratio for the subscripts will be 1 to 1. So write the formula for the ionic compound magnesium chloride. So try to do this on your own before you look at the steps, but come back and then we'll go through it together. So first we need to know the charge of the ion formed by magnesium and chlorine, and we'll also review how to name these compounds. But for magnesium and so for the ionic compound formed from magnesium and chlorine, so remember we said that we can look at trends in the periodic table according to group number. So magnesium is in group 2, so it forms a 2 plus ion, and chlorine is in group 7, so it forms a -1 anion. So write the two ions, and then we crisscross the charge, and so we get MgCl2. So MgCl2. Okay, your turn. Write the formula for the ionic compound that is formed from the following ions: sodium and phosphorus, beryllium and phosphorus, aluminum, and phosphorus. So pause the video, then come back. Okay, so we crisscross. So Na3P. We crisscross again. Be3P2. And essentially we crisscross, but if we remember, when the charges are equal in magnitude, then the simplest whole number ratios will be 1 to 1. So now we want to name ionic compounds, starting with what we call binary ionic compounds. And so in a binary ionic compound, essentially we just have one type of metal ion and one type of non-metal anion. So we just have one element that forms the cation and one element that forms the anion. So a binary compound is a compound in which only two different elements are present. So two different elements. Binary means two. And then in a binary ionic compound, we have two different elements, but one of the elements present is a metal, and the other element present is a non-metal. So the metal is always the positive ion or cation, and the non-metal is always the negative ion. So which of the following would be classified as binary ionic compounds? So take a minute, decide, and then come back. So all of these are binary compounds because they're made up of exactly two different elements, but not all have a metal and a non-metal. So for example, carbon is a non-metal as well as oxygen. So how do we know? Those are both found on the right side of the periodic table. Magnesium is a metal. Chlorine is a non-metal, so that's a binary ionic compound. Iron is a transition metal, so that's a metal. And oxygen is a non-metal, so that's a binary ionic compound. Phosphorus is a non-metal, and fluorine is a non-metal, so that's not a binary ionic compound. But how do we name binary ionic compounds? So we have a metal and a non-metal. The name of the metal stays the same. We change the name of the non-metal. We give it the ending "ide." So bromine becomes bromide, chlorine becomes chloride, fluorine becomes fluoride, iodine, iodide, nitrogen, nitride, oxygen, oxide, phosphorus, phosphide, sulfur, sulfide. So you write the name of the metallic element first, followed by a separate word containing the stem of the non-metallic element and the suffix "ide." So like we were saying, magnesium, and then if it's paired with chlorine, we change the ending of chlorine to chloride. So sodium, and we paired that with the anion of fluorine, sodium fluoride. Magnesium chloride. Okay, so name the following binary ionic compounds. You know the drill. Pause it, come back. So this would be sodium sulfide, beryllium oxide, lithium phosphide, barium iodide. Okay, so we talked about elements that follow patterns based on their position on the periodic table in terms of the charges that they form. So the group 1 elements form group +1 cations. However, some metals, more specifically transition metals, can form ions of different charge. So that means, or another way of saying that, they can form ions with variable charge. So some metals can have varying or variable ionic charges. So that is, for example, iron can form a cation with a +2 charge, or a cation with a +3 charge. And so when we name compounds that contain metals with variable ionic charges, we use Roman numerals to specify the ionic charge of the metal. So that is, the Roman numeral is equal to the charge. So the Roman numeral is equal to the charge. So if we know the Roman numeral, we know the charge of the ion. Or if we know the charge, then we write that as the Roman numeral. And so Roman numerals 1, 2, 3, 4, 5. And so those are likely the most common ones that you will encounter, but especially 1, 2, or 3. The chromium, so chromium 2+, we call that, or when we write the name, we would indicate that as chromium 2, or chromium 3+, chromium 3. Now again, these are only for the ones that can form ions with variable charge. And so shown here are some of the common ones that can have a variable charge. So silver is always going to be +1, but chromium, iron, cobalt, copper 1 and copper 2, tin, lead, mercury, gold. And so I'll try to point these out to you, or make it clear that these can have varying or variable charge. But as you do these, you'll become familiar with the ones that can have a variable charge. Okay, so let's look at an example of how we would name an ionic compound that contains a metal with variable charge. So we need to know the charge, the original charge of the ion. So what we can do is undo the crisscross. So this 2 came from the charge of the cation, and we know that the chlorine, the charge of that is always -1 because it's in group 7. So we're always going to know the charge of one of these, but we don't know the charge of the other. But in this case, we know the charge of chloride, so that's -1, and this would make sense that when we crisscross, it forms CuCl2. So this means that this is copper 2+, and so we would indicate that as copper 2. So we put the charge as a Roman numeral in parentheses. So determine the charge on the cation. So copper 2, and like we did previously, change the ending of the anion, copper 2 chloride. So that's copper 2 chloride. Okay, so see if you can write the formulas of these ionic compounds that contain a metal that has a variable ionic charge, or that can have variable ionic charge. You know the drill. Okay, so let's start here. So copper 1 oxide. So copper 1, so remember the Roman numeral is equal to the charge. So that makes it easy, so you don't have to think about the charge because you know the Roman numeral is equal to the charge. So Cu plus and oxide O2 minus. So you look that up on the periodic table. Oxygen is in group 6. So then we crisscross, and so Cu2O. Copper 2 oxide, Cu2 plus, O2 minus, and so that gives you CuO because we have equal magnitude of charge. Now that is a little counterintuitive because copper 2 oxide has the formula CuO, while copper 1 oxide has the formula Cu2O. But then let's see. So iron 3 chloride, so Fe3 plus and Cl minus, so FeCl3, and iron 2 chloride, FeCl2. So again, write the name of the cation as is. If necessary, specify the charge using Roman numeral in parentheses, and then we change the name of the ending of the anion to "ide." Okay, so name each of the following compounds. Each of these can have variable ionic charge. Now, the hint is think about the charge of the one you know, because this can be a little deceiving. So always think about the charge of the one thing that you do know. Okay, you know the drill. So chloride we know is Cl minus, and then we want to know the charge of chromium, so we can undo the crisscross. So this is chromium 3 chloride. Then, so all of these can have variable charge. So then lead, and then sulfur. So you may be tempted to say lead 1 sulfide, but again, think about what you know. So sulfur is in group 6, so we know its charge is going to be 2 minus. So in order for us to have this formula, we know that we must have equal magnitudes. So this has to be 2 plus. So that would be, and I'll probably do it here, lead 2 sulfide. So be careful. So always think of the charge of the one you do know. Okay, so then again, so we know the charge of oxygen, so O2 minus. So then Pb, so what's the charge? So this one is a little tricky. So when we do this here, so notice that there isn't any subscript here. So what must have happened is this must have been 4 plus, because we reduced to the lowest terms. So we reduced the subscript to in its lowest terms. So Pb 2O4, but then when we reduce, that becomes PbO2. And then, so the name of this would be lead 4 oxide. And so see how the names of the elements are important, because not only should you be able to name them as individual elements, but also as part of compounds. And then this one, so we know Cl minus, and we know, so if we undo the crisscross, this must have been 3 plus. So this would be gold 3 chloride. Okay, another example, and this is kind of similar to the lead 4 oxide example, but now we just have tin 4 oxide. So write the formula for tin 4 oxide. So Sn 4 plus, the Roman numeral equals the charge, and we know oxygen is going to be -2. So then we crisscross, so Sn2O4, but then we reduce to simplest terms, SnO2. Nothing too fancy there. Reduced to simplest terms. Okay, some more examples, so you can go through these if you need additional practice. But now we know how to write formulas for binary ionic compounds and how to name them.